Can you see the screen?
Yes, sir.
Okay. So in the earlier classes, we discussed about the elastic constants. So there are four elastic constants: Young's modulus E, rigidity modulus G, Poisson's ratio mu, and bulk modulus of elasticity K. And we also derived the relationships between them. There were three important relations we derived. By knowing any two, we can find out the other two. So we know that the Young's modulus is the ratio of linear stress to linear strain within elastic limits expressed in Newton per mm square or MPa. Rigidity modulus is the ratio of shear stress to shear strain within elastic limits, once again expressed in Newton per mm square or MPa. Poisson's ratio is the ratio of lateral strain to linear strain within elastic limits, no units for that. And bulk mode of elasticity is the ratio of bulk stress to volumetric strain expressed in Newton per mm square or MPa. And we derived the relationship between them also. See why I am explaining in this type, because you can write down the sketches in your notebook, and whatever material I am presenting here, you can just write down that in your own words, and later on when you come to college, so if you have any doubts, you can clarify those doubts. So here the last topic left in this module 1 is temperature stresses or thermal stresses. So this is also one of the important aspects, because normally all the materials, mainly steel, copper, brass, whatever we deal with instead of materials, they are susceptible to temperature rise or fall. So when there is a rise in temperature, naturally elongation of the material takes place, and when there is fall in temperature, there will be contraction. So that's what is shown in these two diagrams. You can see here there are two bars made of some material, steel, let us say. Suppose if this initial temperature is something like 20 degrees centigrade, and if the temperature is increased by another 20 degrees centigrade, let us say that the temperature has gone to 40 degree centigrade by heating process, then the effect of that will be there will be elongation or increase in length of the bar. Here what I have done is, one end I have taken restraint, that is fixed. So there will not be any elongation this side, but this is a free end. So elongation takes place at this end, and I have taken that elongated length as delta L. That is the increase in length. So when there is rise in temperature, so tensile stress will develop like this. Because of elongation, tensile stress will develop sigma T. That is sigma T. L is the length of the bar, E is Young's modulus of the material of the bar, A is the cross section of the bar, which depends on whether it is circular or rectangular or anything. Similarly, in the other diagram, one end is restrained, and when there is a fall in temperature, when the material gets cooled by some temperature T, then let us say initially it is 40 degree, it is then later on by cooling the temperature has fallen to 20 degrees centigrade, then there will be contraction. So delta L this is the initial length. This is the initial length. L is the initial length. Delta L is the contracted length. So in that case, it will be subjected to compressive stress like this, because contraction in the length takes place. That's what. This is for a simple bar. So later on, we will see how in a compound bar this temperature effect will be. So to understand the normally the question will be asked in such a case will be, what is the value of the stresses that are going to develop and corresponding change in length or elongation or contraction. So I will take T1 as the initial temperature, T2 as the final temperature. Okay, T1 initial temperature in degree centigrade, T2 final temperature in degree centigrade. Difference in the rise or fall depends on, suppose if T1 is greater than T2, then it is fall in temperature. If T2 is greater than T1, that is rise in temperature. Okay. So according to that, you will be having contraction or elongation. So the experiments have been proved that this elongation delta L or the change in length delta L is directly proportional to length and change in temperature. Okay, whether it is elongation or contraction delta L, it is directly proportional to length of the bar and change in temperature. So length of the bar and change in temperature. So as the length increases, your elongation also will increase. As the temperature reduces or increases, the elongation or contraction also will increase or decrease. That is the meaning. Okay. Now, deformation is directly proportional to the length of the bar and change in temperature. That's what I have written mathematically here. Now, if you remove this variation sign symbol, delta L is equal to, it becomes is equal to alpha into L into T. So that alpha is called as the coefficient of thermal expansion. So this variation symbol, if you replace it by an equation, so you have to introduce a constant. That constant is alpha. So alpha into L into T. So that is the, if you please note down that delta L is equal to alpha into L into T. So you should be very careful about the units. So alpha is expressed as per degree centigrade. That means whatever expansion has taken place, that is expressed as a strain there per degree centigrade. So in 1 degree centigrade temperature, change in temperature, what is the corresponding strain? That is called as your coefficient of thermal expansion. So the values are given here. So for steel, alpha value is 12 into 10 power minus 6 per degree centigrade. Okay, for copper, 17.5 or 18 into 10 power minus 6 per degree centigrade. For brass, this is the value. For aluminum, this is the value. That means for it all depends on the type of the material of the bar. Okay. Now here, if you observe this, what you can infer? Aluminium is got the highest value. Okay. The meaning of that is it is more susceptible to temperature. If there is 1 degree rise in temperature, then elongation or that linear strain, whatever it is going to take place in that aluminium bar, it will be this much. Very small number, 10 to the power minus 6. It's a very small number. So this depends on the type of the material. Now, alpha into L into T gives the expression for the elongation or contraction when a bar is subjected to temperature rise or fall. So that is very important. So delta L normally it will be expressed in millimeters. Alpha is expressed as number per degree centigrade. Then L will be expressed in millimeters. T will be in degree centigrade. So if you substitute the units, alpha per degree centigrade into L will be millimeter, into T will be degree centigrade. So degree centigrade will get cancelled. If it get cancelled, you will be getting only mm. So delta L will be expressed in millimeter, very small number. Now in this, you will see there are three cases. You have to understand these three cases. Please note on the diagram here. If the bar is allowed to deform freely, so what do you mean by that? Freely. That means one side I have taken free, another side it is restrained. See here. One side it is fixed or restrained. So the meaning of that is there is no deformation or elongation or contraction on this side of the bar. It can only elongate or contract on this side. On this side. Let me take L as the length of the bar. T is the change in temperature or increase in temperature. Let us say there is an increase in temperature. Alpha is the coefficient of thermal expansion. So due to temperature rise, there develops a tensile stress sigma T. Sigma T is tensile rise in temperature. So when the bar is heated, there will be rise in temperature and tensile stress will develop. And the expression for the elongation is this. So delta L is equal to alpha TL, that has been proved. So delta L can be written as PL by AE. So this is the first derivation we have derived in strength of materials for a uniform rod. When it is subjected to a force P with area A, L is the length of the bar, E is Young's modulus. Its deformation is given by PL by AE. So that is your delta L. So this P by A can be written as sigma. That is the stress. Resistance divided by cross-sectional area is nothing but sigma. So here if you replace P by A by sigma, it will be sigma L by E is equal to alpha TL. Or you can write it as, so L and L will get cancelled. So sigma is equal to alpha into T into E. So this is the expression for the stress, thermal stress. You can call it as thermal stress. So sigma is nothing but here thermal stress. When there is a rise in temperature, or a fall in temperature. So with free expansion or contraction, so one side is free, so then the expression for stress is this. So you have to remember this expression for doing problems. Okay. Then second case is, suppose if the bar is restrained for deformation. What do you mean by that? So it is fixed at both the ends. See here, here it is restrained, here also it is restrained. In that case, suppose if the bar is heated or cooled, there will be either elongation, there should be either elongation or compression, but because of this restrained condition, there develops a opposite type of stress. What happens? Now, let us say there is a rise in temperature. The restrained bar is subjected to rise in temperature. So if it were free, suppose if the ends are free, then it would have been expanded. But here the ends are restrained here, fixed here. That means the ends cannot expand. In that case, to have the equilibrium of the bar, there should develop a compressive stress here. Please understand this. Here it is tensile stress. At free end it is tensile stress, but at fixed end, there should, instead of, because suppose if this is not there, there would have been an increase in the length, but that is restricted here. So to avoid that tensile stress, they should develop a compressive stress of same magnitude. So sigma C is the compressive stress. So when there is a rise in temperature, at restrained end, there develops a compressive stress. Opposite to that, when there is fall in temperature, see here, when there is fall in temperature, naturally the bar should contract. But what happens at the restrained end? There develops a tensile stress opposite. So see here. So that is the difference between this and this. When the ends are restrained, opposite nature of stress will develop. When it is free, so same kind of stress will develop. That is the meaning. Okay. Now here also stress is given by alpha T into E. Same formula. So there is no change in this. Next, the third one is partially restrained. When this partially restrained means, normally this you can see in the form in rails. In rails, you can see this. So here, see here, one end is fixed here. At the other end, what happens? There will be a gap. That gap is called as a clearance. Delta. It is denoted by delta. Delta is called the gap or the allowance or clearance. There is another word called clearance. So it is partially restrained. That means one end it is restrained. On the other end, there is a gap here. Gap will be provided. This gap is provided just to have that expansion of that steel when there is rising temperature. Normally, in the case of rails, during summer, temperature will increase. Due to that, there will be a expansion in that rails. Okay. So to accommodate that expansion, small gap is, this gap will be very, very small, maybe 0.01 mm, something like that. Okay. The gap will be very, very small, delta. So in this case, we call this as partially restrained. In the case of partially restrained condition, see here what happens when there is a rise in temperature. Once again, I take the case of rising temperature. So initial length is this much. Initial length is this much plus delta is the clearance. Delta is the clearance. Then suppose if there is rise in temperature, so delta L will take place. Delta L will be alpha TL. See, alpha TL will be from here to here. From here to here, whereas delta L is only this much from here to here. Please see the diagram clearly. So delta L is from here to here. Alpha TL is from this end, from this free end to this. So then what is the relation then? So delta L is equal to alpha TL minus small delta. See here. This is the relation. So you can see the diagram. So delta L is from this fixed end to this. Alpha TL minus delta gives the value of delta L. So if you simplify this, what we know that stress is equal to strain into Young's modulus. Same relation that holds good for any elastic material. So stress is equal to strain into Young's modulus. So here only thing is in the place of delta L, we have to put this alpha TL minus delta. When it is partially restrained, so we have to take delta L as this much. That is the difference. So delta L is alpha TL minus delta divided by L into E. That's what. This is the stress that is going to develop compressive stress. Naturally, because there is a restriction here. Restraint is their opposite nature stress will develop. Rising temperature means tensile stress would have been developed, but since there is restriction, opposite nature is compressive stress is going to develop. So sigma C in this case is given by this. So these are the three important cases you should remember whenever a temperature stress problem is given. First one is free expansion. When the body is allowed to expand freely or contract freely, stress, whether it is tensile stress or compressive stress, it is given by alpha TL. Alpha TL. Next, when the alpha TE, sorry, alpha TE, when the bar is restrained at both the ends, then also it is alpha TE, but opposite nature of stress will develop. When it is partially restrained, this is the expression alpha TL minus delta by L into E. So you have to remember these three formulae when you are doing problem. Okay, this is about the temperature stress in simple bars. Simple bars. Now let us see one problem in which case in this problem all the cases will we are going to handle. So let us see how those three formulae can be applied to solve this problem. Understand the problem first. Please note down this problem in your book. A railway is laid so that there is no stress in rails at 8 degrees centigrade. That means it is initial temperature is 8 degrees centigrade. So this is 8 degrees centigrade. So it is laid when there is no stress. It is laid. That means at 8 degrees centigrade, the railway line is laid. But what happens? The temperature goes on increasing. So calculate stress on the rails at 50 degrees centigrade. So when the temperature rises to 50 degrees centigrade, what is the stress in that temperature stress that is going to develop in those rails? That is the question. If there is no allowance for expansion, so that is the first case. If there is no allowance for expansion means there is no end is free end. So it is not sorry, the end is fixed end. There is no allowance expansion means it is fixed end. Fixed end. Okay. So that is the first case. That is delta is equal to 0. That is the meaning. There is no allowance for expansion means it is not a free end. It is a fixed end. Stress on the second case, stress on rails at 50 degrees centigrade only. If there is an expansion allowance of 8 mm per rail, suppose if there is an expansion allowance, delta value 8 mm, 8 mm is there provided, then what is the value of thermal stress in that second case? Third case, the expansion allowance, if the stress in the rail is to be zero when temperature is 50 degrees centigrade. That means how much that the rail can be given an expansion allowance so that the stress in the rail is zero. There should not be any thermal stress in the rail. That is the third case. Last one, maximum temperature to have no stress in the rail. That means there should not be any stress in the rail if the expansion allowance is 12 mm per rail. So expansion on a delta is given as 12 mm. So what should be the maximum what can be the maximum temperature that there are no stresses that are going to develop in the rail. So length of the rail is given as 30 meters long, L value, alpha, coefficient of thermal expansion, 12 into 10 power minus 6 per degree centigrade, Young's modulus, 2 into 10 power 5 MPa, that means it is T. So once you know the value of alpha and E, you can decide the material. Okay. So understand this problem. This is a simple problem, but there are 4 cases in that. So one by one you will understand. So when the rail is laid at 8 degrees centigrade, so there was no stress. Okay, that is initial temperature. When the temperature is raised to 50 degrees centigrade, so the change in temperature or rise in temperature becomes now 42. 50 minus 8, 42 degrees. So what is the corresponding stress? So I told, so this is the case of both the ends restrained. So when there is no free expansion means when the bar is restrained. Restrained. There is no expansion. It is fixed. Fixity condition is there at both the ends. So we have to use the same formula alpha TE. But the thing is, it develops a opposite kind of stress. Compressive stress will be developed. So temperature stress will be compressive in nature here. Rise in temperature is there, but temperature stress will be compressive in nature. Now use the formula alpha TE. That's all. The first step is alpha TE. So sigma is equal to alpha TE. Alpha value 12 into 10 power minus 6. T is change in temperature, a rise in temperature 42 degrees centigrade. into E value 2 into 10 power 5. So we should be very careful when you are substituting in the formula. So we have to stick on to the SI units. So E should be Newton per mm square or MPa. T should be in degree centigrade, and alpha will be naturally per degree centigrade. When you substitute and simplify, you will get the compressive stress because there is rise in temperature. Since the restraint condition is there, temperature will be compressive, opposite nature. So 100.8 MPa Newton per mm square is the temperature stress that is going to develop in the first case. Okay, then second case, stress on the rails at 8 at 50 degree centigrade if there is an expansion variance of 8 mm per rail. So in this case, it is partially restrained. See, third case, partially restrained means we have to use this formula. Here, delta is 8 mm. 8 mm has given. Okay, other uh, constants remain the same. Delta is an additional thing. So we have to use that formula. See here, sigma is equal to delta L by L into E, where delta L is alpha TL minus delta, small delta, divided by L into E. So substitute. So alpha is 12 into 10 power minus 6, E is 42, L is 30 meters. Please note, 30 meters I have converted to millimeters. So it should be in millimeters. Whenever you are substituting the formula, convert meters to millimeters. So 30 into 10 power 3, 30 meters minus 8 mm. So this entire thing you have to multiply minus 8 divided by L is 30 into 10 power 3 in millimeters. So into E means 2 into 10 power 5. So this is what I have, you have to substitute. Now if you simplify that, you will get 47.47 MPa. So once again, so you are getting that value as compressive stress because it is restrained. Restrained. See, you see this diagram. See this diagram. Here you can see this is compressive in nature. Okay. Rising temperature gives a compressive stress. Next, coming to the third one. Third one is the expansion allowance if the stress in the rail is to be zero, which then temperature is 50 degrees centigrade. So stress should be zero. So sigma should be zero. What should be the allowance that can be provided? Delta is unknown. See, once again, you have to use this formula only. Partially restrained formula. Only thing is delta is unknown here. Same formula you substitute. Alpha TL minus delta by L into E. If you use the same formula, so since sigma is 0 here, so this should be 0. Here E cannot be 0. Therefore, this can be taken 0. Alpha TL minus delta by L can be taken it as 0. So from that, if you substitute the values, you will get delta as 15.12 mm. Please do that. You just check it. So substitute for alpha 12 into 10 power minus 6. T is 42 degrees centigrade and delta is unknown. L is 30 into 10 power 3. So if you substitute that, you will get the allowance 15.12 mm. What is the meaning of that? So that means if you give an allowance of 15.12 mm, if you provide in this figure, let me say this is the rail, let us take. If you provide the delta is equal to, if you provide a allowance of 15.12 mm, then your sigma is 0. This bar is not at all subjected to any thermal stress. That is the meaning. Okay. So that is the maximum allowance you can provide to have zero stress. Now the fourth one is, it is similar to this one only. In the fourth case, what happens? Temperature we have to find out. Till what temperature we can rise? We can rise so that no stresses will develop, but expansion is fixed here. That is, sorry, allowance is fixed, 12 mm. So if delta is equal to 12 mm, what is the maximum temperature up to which that rail can be heated? That means what is the maximum temperature that rail can take? So for that, so delta is given as 12 mm. Sigma once again it is 0. No stress should develop. What is the maximum temperature? Tm. In this Tm means it is T2 here. Initial temperature is 8 degrees centigrade. That is known. So what is the final temperature means? Maximum temperature Tm we have to find out. So use the same formula. Use the same formula here. So once again we have to take sigma as 0. E cannot be 0. Therefore this should be 0. Here delta is known 12 mm, L is 30 into 10 power 3 millimeter, alpha is 12 into 10 power minus 6, T you can find out. So this is the maximum temperature, Tm or T2 you can take, T2 that is the T2. T2 will be 33.33 degree you are going to get after simplification. That means T2 value is 33.33. So T2 minus T1 is T here, that is change in temperature. So therefore, we have this 33.33 is the value of T, change in temperature. So change in temperature is equal to final temperature is T2 minus 8 degree. So therefore, T2 will be equal to that is 41.33 degrees centigrade. The meaning of this is from 8 degree till 41.33 degrees centigrade. So that rail can get the rise in temperature so that stresses are zero, allowing a gap of 12 mm. So these are the types of I have explained. So all the four cases, see here. First case, pre-expansion. Second case, both the ends are restrained. Third case, partially restrained. So any one of these can be unknown. Stress can be unknown, temperature can be unknown, allowance can be unknown. So these three are the unknown. So temperature, stress, allowance. In the same problem, all the four cases have been taken care. So this is the case of a simple bar. Only one bar is there, When only one bar is there, how that temperature stresses can be found out. So same thing can be adopted for compound bars. Compound bars. So compound bar means when the system has got more than one material. So of same length or different lengths. Okay, that is also important. Area may be different, length may be different. So Young's modulus value will be different. Forces carried by the two bars will be different. So we have discussed about compound bars in the earlier class. We had discussed in the earlier classes. We had found out the stresses in the compound bars using two conditions of equilibrium. So two conditions. What is the first one is the equilibrium condition, that is the whatever force is acting on the system that will be shared by the bars, that is P is equal to P1 plus P2 plus P3 like that. So using that you can write in terms of stresses. So P can be replaced by sigma into A. That's what I had explained. Next, second condition was strain compatibility condition, where we have used that the strain that is change in length in all the bars will be same. So delta L1 is equal to delta L2 is equal to delta L3. So that's what we have used for solving problems of compound bars earlier. Now the same thing can be utilized, same conditions can be applied for solving problems in the case of compound bars also subjected to temperature stress. So here, please write down the diagram neatly. So there are two bars here. See, bar 1, bar 2 I have taken of different materials. One may be steel, another may be copper, something like that, of same length. Here I have taken same length. But the same concept holds good for different lengths also. Length of bar 1 and length of bar 2, they are same. Area I have taken A1, A2. Let us take area as A1, A2. Length is L1, L2 is equal to L. Length I have taken L. Area is A1, A2. When this is subject, see, this is a compound bar. When there is a rise in temperature, let us say there is a rise in temperature, what happens? These two bars, they will not elongate to the same extent. Please understand this concept. So even though they are free at both the ends, so this is the initial position of the bars, okay? Of the bar, initial position of the, up to this it is L. Up to this is L. Now once these, let us say the first bar is steel. If when this is heated, its length has gone. It has increased. It has increased to the up to here. So that means delta L1. So this is your delta L1. Change in length. Okay. Now, not delta L1. You have taken as delta L. Delta L. So next, the second bar is, let us say, copper bar. It has not elongated to up to the same length. That is very important. So elongation of compound bar, what it will be? It will be somewhere here in between. Somewhere here in between. That means what we have taken is from here to here it has taken as delta L. From one bar will go beyond that, another bar will be contracted. So one bar will be expanded, another bar will be contracted. See here, I have shown here. This is the line. This is the line, common line for both the bars. So when this is expanded, elongation takes place. Naturally, there will be a compressive stress that is going to develop here to bring this to this level. Whereas here, to bring this to this level, so there should be a tensile stress. See, understand this concept here. So this is the common line for the compound bar. This is the common line. Up to this, it has expanded. Let us say now, due to the difference in the values of Young's modulus, cross sectional area, everything. So this has elongated more. This has elongated little bit less when you take individual bars. So have the to have to what you have to do is here, since it has expanded here, to bring to this level to here, there should be a compressive stress here for the first one. There should be a tensile stress for this. That's what you have to understand. Now let us see the change in temperature. Rise in temperature is T here. Once again, T2 minus T1. T2 is the final temperature, T1 is the initial temperature. Difference gives the rise in temperature. Then alpha 1, let us say alpha 1 is greater than alpha 2 here. That means coefficient of thermal expansion of first bar is greater than that of second bar. That is why this has elongated more than this. But when you are dealing with compound bar, you have to take the common expansion you have to take. That's what I will explain now. So alpha 1 is greater than alpha 2. Therefore, bar 1 has expanded more than bar 2. Delta L is the elongation of the compound bar. See, compound bar elongation is from here to here, common line. So beyond that, you have delta L1 for the first bar. Then before that, you have the delta L2 for the second bar. So delta L2 is this distance. See here, this distance is delta L2, and this distance is delta L1. Please make a note. Now what we have to do is, for the equilibrium of the compound bar, delta L of this and delta L of this, they should be equal. That means if you take this upper bar, let us say upper bar, what is delta L? Delta L is alpha 1 TL. So alpha 1 TL is this full thing from here to here. From here, suppose the meaning of that is, suppose let us assume that there is only one bar. Bar 1 only is there. Then what is its expansion? Alpha 1 TL. That is its expansion. Suppose if only bar 2 is there without bar 1, then what is its expansion? Alpha 2 TL. That is its expansion. Okay. So that is the free expansion, we can say. So from here to here, it is alpha 1 TL minus delta L1 gives the value of delta L in the first bar. Second bar, alpha 2 TL is from here to here for only this bar, from here to here, plus delta L2 we have to take. So see, so to get delta L, alpha 2 TL plus delta L2. So that's what I have written here. So delta L is equal to alpha 1 TL minus delta L1 from the first bar, or it is also equal to alpha 2 TL plus delta L2 from the second bar. See here, these two should be equal. So this is your compatibility condition. Okay, delta L, whether you are calculating from first or second, it should be equal. So please note that if you are taking only bar 1, this is the expansion. Alpha 1 TL is the expansion. If you take only bar 2, expansion is free expansion. That is called as free expansion, alpha 2 TL. But since it is a compound bar, we have to take somewhere here due to compatibility, and we are equating the delta L for both the bars in this fashion. This is the mathematical representation of the deformation for both the bars. So now you can say that what is the delta L1? Delta L1 is P1L by A1 E1. So PL by AE is delta L, we have seen that, we have derived it, fundamental equation of SOM. Now here P1 L1 by A1 E1 can be here. P1 by A1 is nothing but your sigma 1. That is the stress in the first bar. Okay, and similarly delta L2 is P2L by A2. Here L1 and L2 they are equal. So that is equal to L. That's why I have written L here. Now if you substitute this there, so what happens? Substitute for delta L1 and delta L2. In this, you will get delta L is equal to alpha 1 TL minus P1L by A1 E1. That is equal to alpha 2 TL plus P2L by A2 E2. Now here, what is this P1 and P2? So P1 is the force that is going to develop in this bar, compressive force. See, I have shown here. Sigma 1 is the compressive stress. P1 is the compressive force that is going to develop. This P1 is nothing but sigma 1 into A1, because stress is equal to resistance divided by area. Resistance is stress into area. So sigma 1 into A1 is your P1. Here it is tension. So to bring this bar to this level, they should develop a tensile stress here. So P2 is the tensile force or resistance force. So that we will be getting P2 is equal to sigma 2 into A2. Sigma 2 into A2. So that means if you substitute here, so you'll get this equation. So same thing, this equation is known as compatibility equation. So this is very, very important for doing problems of compound bars subjected to temperature stresses. We are using this compatibility equation. We are using this compatibility equation. Okay. Now, so that's what I told. Sigma 1 is compressive stress. Sigma 2 is tensile stress. P1 by A1 is the compressive stress. P2 by A2 is the tensile stress. So P1 and P2, they are the internal forces that are going to develop in those bars. P1 is compressive force, P2 is tensile force. So for equilibrium condition, these two should be equal. Okay, there is no addition, any other force acting on the bar. So for equilibrium, these two forces should be equal. One bar is subject to tension, another bar is subject to compression. Totally, the effect should be zero. So each one of them should nullify the effect. So P1 is equal to P2. That means sigma 1 A1 should be equal to sigma 2 A2 in the case of compound bars. So this is the equilibrium equation. So this is compatibility equation. This is equilibrium equation. So similar equations we got earlier also when it is subjected to only axial force. We have done problems of compound bars subjected to axial forces. This is compound bar subjected to temperature stresses. Okay. So these two you should remember. So you should remember these two equations for solving problems on compound bars. One is the equilibrium equation, which says that the force developed in the two bars in the tensile force and compressive forces that are going to develop in the system of bars, they should be equal. That is our equilibrium equation. And compatibility equation says that irrespective of whether any type of material in compound bar, your elongation, that is elongation or contraction, that is change in deformation, it remains same in both the bars. That is your compatibility equation. So this is the equation for compatibility. This is the equation for equilibrium. So these two we have to write down. So unknowns are sigma 1 and sigma 2. Please note that in these problems, all the values will be given except sigma 1 and sigma 2 will be the unknowns. We have to find out the stresses. So there are two unknowns, two equations we can solve. Alpha 1, alpha 2, T, L. So E1, E2, they all will be given. A1, A2 also will be knowing. So from the second equation, you can express sigma 1 in terms of sigma 2, and that you can substitute in the first equation to get to solve the two equations to get the values of sigma 1 and sigma 2. So that's what I have written here. From equations 1 and 2, stresses sigma 1 and sigma 2 are found out. If the bars are of different lengths, only change is instead of using L, so you have to use L1, L2. L cannot be cancelled out. If the bars are having same length, here you can cancel out this L. But if the bars are of different length, then we have to keep it as L1 and L2, and the equations will be same like this. So alpha 1 T L1 instead of L, that will be L1 minus sigma 1 L1 by E1. Actually, this is P1 by A1. P1 by A1 is nothing but your sigma 1. P2 by A2 is nothing but sigma 2. So this is what the equation we get, compatibility equation when they have different lengths. And of course, equilibrium equation remains the same. So only compatibility equation changes. So this is very, very important. Compound bar. Once again, I will just explain you compound bars temperature stresses. So whenever you have two different materials combined together, it is a compound bar. It is the system is subjected to rising temperature or falling temperature. So since the Young's modulus is different, the coefficient of thermal expansion values are different for both the materials. Each bar will have its own expansion. So free expansion for the first bar is alpha 1 TL. For the second bar it is alpha 2 TL. So they will be different. So since it is a combined system, we should have a common we should have a common expansion, that is delta L. So that delta L can be expressed for both the bars separately. By considering this figure, you can see that you have to come to this common delta L. This should develop a compressive stress. This should develop a tensile stress. So sigma 1, sigma 2 are the compressive and tensile stresses. Corresponding forces are P1 and P2. P1 is sigma 1 into A1. P2 is sigma 2 into A2. Now, from the diagram, you can write the expression for delta L for the first bar as well as for the second bar. So, from here to here, this is the common expansion. So, common expansion delta L is this total free expansion minus delta L1, and here this total free expansion plus delta L2. So, that's what I have written here. So, we have got this equation. This is the compatibility equation. Second equation is the equilibrium equation, which says that the forces developed, tensile force and the compressive force developed in the bars, they will be equal numerically. So for equilibrium. So if you use that, P1 is equal to P2. In this case, P1 is compressive, P2 is tensile. So if you substitute that in terms of stresses, sigma 1 A1 is equal to sigma 2 A2. By solving these two equations, you can find out the unknown sigma 1 and sigma 2, and later on you can find out delta L also. Once you get the value of sigma 1 sigma 2 by solving these two equations, substitute that sigma 1 sigma 2 here and get the value of delta L. So that is when the lengths are different, then you have to use this formula. So one problem I will explain on this compound bar now. So we have to use two conditions because there are two unknowns. We require two conditions definitely to solve the problem. Sigma 1, sigma 2 are the unknowns, and the two conditions available are one is equilibrium condition, another one is compatibility condition. Okay. Now see this problem. So please write down this diagram. So here there are two copper bars. So the first one and last one are copper bars. Area of the copper bars are 150 millimeter square. You write down the sketch. The remaining you can understand here. Then this is steel bar with area 1200 mm square. See, please note that. Sorry, 120 millimeter square. 120 millimeter square is the area of steel bar. 150 millimeter square is the area of copper bars. There are two copper bars, and length of copper bars are 240 mm. Length of steel bar is 150 mm. 180 mm. Please make a note of that. So this is 180 mm. Length of steel bar is 180 mm. Area is 120 millimeter square. Length of copper bar is 240 mm. Area is 150 mm. Okay, there are two copper bars here. So that is totally there are three bars. One steel bar and two copper bars. This is the arrangement. The question is, determine the stresses and deformations induced in the bars if the temperature is increased by 70 degrees centigrade. Take ES as 2 into 10 power 5 MPa, that is Young's modulus for steel. E of copper 1.2 into 10 power 5 MPa, it is less than that of steel. You can see alpha is coefficient of thermal expansion of our steel 12 into 10 power minus 6 per degree centigrade. For copper 18 into 10 power minus 6 per degree centigrade. So that's what the problem is. Now here he has given Young's modulus of steel and copper, alpha values for steel and copper. Rise in temperature he has given. He has not given initial temperature and final temperature. Instead of that, he has given rise in temperature. Maybe from 10 degree to 80 degree or 20 degree to 90 degree, that rise has taken place. So only we are interested in T value. And Here, the one thing is alpha C is greater than alpha S. See here, alpha C is greater than alpha S. So coefficient of thermal expansion of copper 18 into 10 power minus 6. This is 12 into 10 power minus 6 per degree centigrade. So alpha C is greater than alpha S. So naturally what happens? Copper is subject to compressive stress. So what I told so it is reverse. See here in this diagram, now you can take the first one as copper, second one as steel. So since alpha is more for copper, this you can take it as copper, this you can take it as steel, like that. Okay. So naturally, this will be subjected to compression. This will be subjected to tension. That's what I have written here. So copper is subjected to compressive temperature, compressive stress, and steel is subjected to temperature, tensile stress. Okay, subjected to tensile stress. This is subject to compressive stress. So that means PC and sigma C, they are compressive. In copper, force induced in copper bar is PC, compressive force. Sigma C is the compressive stress in copper. Then PS sigma S, force induced in steel bar is PS, tension. And sigma S is the stress induced in steel, that is tensile stress. Okay. Now we have to use these two equations only. One is equilibrium equation, another one is the compatibility equation C. So these two we have to use. So P1 is equal to P2, then this one. Because the lengths are different here, we have to use this one, L1, L2, in terms of L1, L2. But here, what happens if you observe there are three bars here, two copper bars and one steel bar. So what you can say here is in copper bar, so you have got PC force. In steel bar, you have got PS force induced. Okay. So the meaning of that is you are in the entire system, whatever total compressive force is going to develop, that should be equal to total tensile force that is going to develop. Here there are two copper bars here, first and last. So in these two copper bars, 2 times PC I have to write now because there are two copper bars. 2 times PC should be equal to PS because only one steel bar is there. So force induced in this is PS, force induced in this is PC, force induced in this is PC. So the meaning of that is 2 times PC should be equal to PS. So because tensile force in steel should balance with the compressive forces developed in copper. So that's what I have written here. So PS is equal to 2 times PC. So what is PS? PS is sigma S into AS. Force is equal to stress into area in steel. So PC is sigma C into AC. That's what I have written here. Now substitute the values, known values. Sigma S is unknown. AS, area of steel rod is 120 millimeter square. It is given. So substitute as 120 into sigma S is equal to 2 times 150. Sigma C is 150. AC is 150. AC is 150. Area of copper is 150. So 2 into 150 into sigma C. So you will be getting sigma S is equal to 2.5 times sigma C. So from the equilibrium condition, you are getting the relationship between the stresses in steel and copper as this one equation. Next, compatibility equation. So we have to use this one. So since the lengths are different, we have to use this. So here, please note that. So alpha 1 is copper, 2 is steel. So alpha 1 is alpha C, L1 is LC, length of copper. Okay. Sigma 1 is sigma C. That's all. So here also alpha 2 is alpha S. Okay. So L2 is LS and sigma 2 is sigma S. E2 is ES, E1 is EC. So the same equation is used now, compatibility condition equation. So I have written that here. See, alpha 1 T L1 means alpha C T LC minus sigma C LC divided by EC should be equal to alpha S plus LS plus sigma C LS divided by ES. So this thing, one side it is minus, another side it is plus. That is the difference. This we have proved from this diagram. So you can see this geometry of this diagram. From this we have written that. Okay. So this is the fundamental diagram, basic diagram for understanding the compound bar's temperature stress. Yes. Now if you substitute that here, what happens? So this is also delta L. This is also delta L. But expressed in terms of copper, this is expressed in terms of steel. So in this, you whatever known things are there, you all substitute that. So alpha C is 18 into 10 power minus 6. So into T is 70 degrees centigrade, change in temperature. LC, length of copper rod is 240 minus sigma C is unknown. LC, length of copper is 240 mm divided by EC is 1.2 10 power 5 given value is equal to alpha S is 12 into 10 power minus 6. T is once again 70. LS is 180 mm plus sigma S. Okay, this is sigma S into 150 mm is length of this thing divided by 2 into 10 power 5. So if you simplify this all this, you will be getting something like this. One some constant term along with the sigma C term in LHS, constant term along with sigma S term in RHS. Then what you have to do is this you have to put in the place of sigma S. Now we have to solve these two equations. We have to solve these two equations. Two unknowns are there, sigma S and sigma C. So to solve that, substitute for sigma S as 2.5 sigma C in this equation and simplify. You will get only one unknown as sigma C that you are going to get 35.576 something Newton per mm square. This is compressive. It is compressive. So this stress is compressive stress. Now put that value here, 2.5 times this will give the stress in steel which is tensile. So the tensile and compressive we have to decide based on the value of alpha. So copper will elongate more, so it is subjected to compressive, because opposite effect, to bring back to the common change in deformation. So compressive stress will develop, whereas for steel, it won't elongate much, therefore it should be subject to tensile stress. So sigma S tensile, sigma C compressive. Now, if since he has asked what is the deformation of the compound bar, for that we have to use either this or this term. So these both are equal to delta L. LHS term or RHS term, both are equal to delta L. So either you can use this or this. So here, whether you use this or that, you should get the same answer. That's a check. So delta L, I am using C. Either you can use this term, LHS term or RHS term in terms of steel or in terms of copper. So you know now sigma C value, you know all these values, you know already given values. Otherwise you can use this sigma S value is this much. So either you can substitute in this or this, you can get the value, the common value 0.2312 mm you are going to get. So normally the values are expressed to minimum 3 digits because 3 decimals, because its a value is very small. When the value deformations, all those things will be strains will be very small. It is better to express after the decimal point up to 3 digits. So here I have given to 4 digits, 0.2312 mm. So this is a problem which explains the temperature stresses in compound bars. So let me once again go through first. So this one steel bar is there, two copper rods are there, 240 mm and 150 mm square for copper, 180 mm and 120 mm square for steel, length and areas. Okay. So since this coefficient of thermal expansion of copper is more, alpha C is greater than alpha S, so copper will elongate more if it is free. So then to bring back to the compound that is a common change in length, it should be compressed. So that is why compressive stress will develop in copper. Oppositely, steel bar is subject to tensile stress. Now we are using two conditions for finding the stresses. One is equilibrium condition, other is compatibility condition. There are three bars. One bar is steel, force developed in that tensile force developed in the steel is PS. Compressive force developed in copper will be PC. So equilibrium equation is PS is equal to 2 times PC because there are two copper bars. So that if we express in terms of stresses, so this is PS, this is PC. So PS is equal to 2 times PC. Expressed in terms of stress and area, you are going to get the relationship between the stress in steel and stress in copper. Then compatibility condition, your total deformation remains same in a compound bar, irrespective of the number of materials used. So using that concept, so copper is subjected to compressive stress. This is the expression for delta L in terms of copper. This is the expression for delta L in terms of steel. So once again, if you substitute the known values, so sigma C, sigma S will be unknown. Now we have got two equations for to solve for sigma S and sigma C. So substitute the sigma S is equal to 2.5 times sigma C in this and solve. you will get sigma c here. So substitute that sigma c once again here, you will get sigma s. So nature will be different. Sigma c is compressive, sigma s is tensile. Then since he has asked the deformation of the compound bar also, then delta L also we have to find out either by using copper equation or steel equation. So you should get the same answer. So whether you use this or this, you will get the same answer 0.2312 mm. So this is what I wanted to explain you today. So some more examples I'll be taking in the next class. So this is the I think another one class I will be completing this module one. Module one. So module one, as I already told, is a very big module. Simple system strains. Lot of things we have covered. Simple bar subjected to tensile stress, compressive stress, shear stress, then self weight, elongation due to self weight, then compound bars, stepped bars, so tapering bars, all those things we have covered. Then we discussed about generalized Hooke's law, problems on that. Then we discussed about the elastic constants, relationship between them, and problems on finding elastic constants. And today we have discussing about the temperature stresses. In that also, once again, simple bars and compound bars. Okay. So I think next class I will continue. If you have any doubt, you can ask me. But these sketches, I advise you to redraw the sketches in your notes. So I will be seeing the notes once you start coming to college. I want you to submit your notes also. So diagrams and all, you please write it clearly. Same problems, you try to work it out, and additional problems I am going to give as assignment. Maybe tomorrow I am going to give the first set of assignments. So problems I am going to give. So all the types of problems I am covering, but you have to work. Unless you work, so you will not be getting any no. So concept you have to clearly understand. So any doubt is there, you can ask me. Are you awake, students?
Yes, sir.
Hmm. I thought. Okay. So we have to work. Today's concept. Did you understand temperature concept? Nobody is answering. Did you understand the temperature concept?
Yes,
Temperature
sir.
stresses. Okay. When you start studying, you will be getting doubts at that time. Okay, I will take the attendance 18028. Tejas, Tejas, Tejas,
Yes, sir.
19002. Abhishek,
Yes, sir.
005. Darshan,
Yes, sir.
006. Divyashri,
Present, sir.
007.
ಸರ್ 003 ಹೇಳಿಲ್ಲ
003 ಹೇಳಿಲ್ವಾ 003 1 second. 003 Ajay Kumar. Okay.
ಸರ್
006 Divyashri.
Yes, sir.
7 Jannavi.
Yes, sir.
Yes. 7 ಆದ್ಮೇಲೆ 10 Padma.
Present, sir.
Then after 10, 11 Preeti.
Present, sir.
12 Rahul.
Present, sir.
13 Medhesh.
Present, sir.
14 Sai Rajaram. Okay.
Present, sir.
16 Srilakshmi.
Present, sir. Present.
17 Shreyas.
Present, sir.
19 Shweta.
Present, sir.
21 Surya.
Yes, sir.
Okay. Anybody left out? So my question is now, are you following this subject or not? Because I am not seeing you people, how you will be. So I want to know because your test next month during first week or second week, maybe test will be maybe first week only, fifth, sixth, seventh. They have given. I don't know. They will announce the timetable. So you should be prepared, well prepared for that. So subject, are you following the subject? Somebody should talk. That means you are not following. Are you not following? Janavi,
Sir.
are you following?
Yes, sir.
Okay, you are telling yes. Abhishek, 002,
Yes, sir.
are you following? You
Yes,
have to
sir.
tell me your opinion because it is online class. We will not be knowing whether you are understanding or not. If it is physical class, we can always come to you and you can ask. It will be individual interaction will be there. But here, it is very difficult to know whether you have understood or not. So that is one problem we are facing. So now that's why you have to study whatever I have explained in that class. That today only you try to finish it off. Otherwise, if you keep on pending, you'll be getting lots of doubts. Okay. Anyway, tomorrow we'll continue. We'll meet. Thank you.